Welcome to the test commentary for question 1 of paper B, the higher tier paper for the Year 10 mock exam. What a mouthful. Right, question 1. Cobalt forms coloured compounds. A pink cobalt compound reacts with hydrochloric acid. The reaction can be represented as pink cobalt compound plus hydrochloric acid plus gives blue cobalt compound and water. And there's our equilibrium arrow. More information. The forward reaction is endothermic. When both cobalt compounds are present in a solution at equilibrium, the equilibrium mixture is purple. So what does all this mean? Right, well, it means that this compound here reacts with hydrochloric acid to make the blue cobalt compound and water, and the blue cobalt compound and water reacts with water to make the pink cobalt compound. So we've got a forward reaction and we've got a backward reaction. And this compound happens to be pink, this compound happens to be blue, so when we've got a mixture of both of them in equilibrium, the overall colour is purple, because when we mix pink with blue, purple is what we get. So what's it going to ask us about this? You've never seen this reaction before, but that doesn't matter. You've been given some information on it, you don't need to know about the formulas or anything, you've been given enough information here to answer the questions that follow. What's meant by equilibrium? So this is a 2-mark definition question, and it's a definition that you're just going to have to learn. An equilibrium is where we have a forward reaction and a backward reaction at the same rate in a closed system. So the first mark is for saying that the rate of the forward reaction is equal to the rate of the reverse action, and the second mark is for saying it's a closed system. Question 2. Now it starts to get difficult. The equilibrium mixture is cooled. What does that mean? Well, it means that some equilibrium torturer like you or me or an experimenter, is taking this equilibrium and cooling it down by putting it in a fridge. They're just going to reduce the temperature surrounding the equilibrium. Explain what happens to the concentration of the pink cobalt compound. Right, so here we go. Here's the, oh sorry about the reflection. Oh God, that's not good. Oh well. Never mind. Sorry about the headlights. Here we've got the pink plus hydrochloric acid, reversible reaction, makes blue cobalt compound and the water. We are told that the forward reaction is endothermic. So going this way is endo, which must mean, obviously, the back reaction is exothermic. So in an endothermic reaction, heat is taken in. So going this way, we're getting colder. In an exothermic reaction, heat is given out. So going this way, we're getting hotter. Now at equilibrium, this reaction is going at a rate equal to this reaction. So heat is being given out at the same rate as heat's been taken in. So at equilibrium, obviously the temperature stays the same. Heat's been taken in at the same rate as heat's been given out. But what we've done is we've tortured this equilibrium, we've cooled it. Okay? We've tried to make the whole thing colder. Now, equilibriums don't want to be disturbed, they always act to oppose the change, don't they? So if I'm making it colder, to oppose the change, the equilibrium wants to be hotter. And the only way it can be hotter is to do more of the backwards reaction, because that's the exothermic reaction giving out heat. So if I cool this equilibrium down, I'm going to get a faster rate of reaction for the backwards reaction because it's exothermic. Now if I get a bigger rate of reaction going backwards than forwards, what's going to happen to the concentrations of the two sides? Well, if we're getting more of this reaction, I'll have a decrease in the amount of blue cobalt compound and decrease in the amount of water, and I'll have an increase in the amount of pink cobalt compound and hydrochloric acid. So getting back to the question, what did it say? Explain what happens to the concentration of the pink cobalt compound. Well, the concentration of the pink cobalt compound is going to increase because the exothermic reverse reaction is going to be favoured. I think that's all we needed to say. We could say because the equilibrium is acting to oppose the change. Question 3. More hydrochloric acid is added. Explain what happens to the colour of the equilibrium mixture. Okay, so look, you've got to, first of all, they've been a bit weaselly. They're asking you about the colour of the equilibrium mixture. So if you don't answer in terms of colour, you're not going to get all the marks. We go back to our equilibrium. Now this time we're not changing, we're not talking about adding things, adding heat or taking heat away. We're not changing the temperature. What we're changing is the concentration of stuff. Right? So it says more hydrochloric acid is added. So I'm going to increase hydrochloric acid. Now, equilibriums act to oppose any change put on them. So if I increase the concentration of hydrochloric acid, the equilibrium is going to say, no, I'm going to oppose that. I'm going to do something to oppose that change, to try and equalise that change. Well, the only way it can oppose that change is to have less hydrochloric acid. And the only way it can make less hydrochloric acid is to do more of the forward reaction. If it does more of the forward reaction, it will reduce the amount of hydrochloric acid. It will try and oppose the change I've put on it. I've increased the hydrochloric acid, it's going to reduce the hydrochloric acid back. If the forward reaction is favoured, like that, it means the concentration of the blue cobalt compound and water is going to increase. So I'm going to get more blue and more water. We won't ask that though. What explains what happens to the colour of the equilibrium mixture? Well, the colour of the equilibrium mixture is going to become more blue, isn't it? It's going to become more blue because the equilibrium is acting to oppose the change, is acting to reduce the amount of hydrochloric acid, so more of the blue compound is made. Question 4. Why does cobalt form different coloured compounds? This is a bit of knowledge going back to the very first unit we did in year 10. Transition metals form different coloured compounds. Their ions form different coloured compounds. It's because it's a transition metal. Question 5. An oxide of cobalt has the formula CO2O3. Notice with cobalt, look, CO2, yeah, CO2O3, how different that is to CO2. CO2 will be carbon dioxide, capital O. CO, little o, is cobalt. Big difference capital letters make in chemistry. We've got to work out, mind you, what the charge on the cobalt ion is going to be. Well, we know that all compounds have neutral charge, no charge overall. So overall, CO2O3 has no overall charge. We also know that it's an ionic compound because it's a metal and a non-metal. And we know that ionic compounds are formed from ions. Now, we can't look up in our periodic table, we can't easily find out what the charge on cobalt is because it's a transition metal and they have variable charges, but we do know about oxygen. We do know that oxygen is in group 6, so it needs 2 electrons to fill its outer shell to get to 8. So each oxygen is going to gain 2 electrons, which makes it an O2- ion. And look, we've got 1, 2, 3 O2- ions in this compound. So the total charge is -6. So if the total charge on the negative ions is -6, we must know that the total charge on the cobalt, the positive ions, must be +6. We've got 2 cobalt ions, CO2, okay, there they are, with a total charge of +6, so +6 divided by 2 is +3. So our answer is +3. Cobalt compounds can act as catalysts. Which 2 statements about cobalt compounds are correct? Right, well this is going to be about their actions as catalysts, so it's a catalytic question, right? And we know that catalysts speed up reactions but are not consumed by them. So that's our basic knowledge about catalysts. They speed up reactions but they're not consumed by them. There's as much catalyst left over at the end of the reaction as we started with. So let's have a look. They allow reactions to reach equilibrium more quickly. So that's about speed, so that's looking pretty good to me. They are reactants in reactions catalyzed by cobalt compounds. Well, no. Catalysts aren't reactants. They're involved in the reaction, but they're not reactants, so that's definitely not right. They are used up when acting as catalysts. We know that's not true. Catalysts are not used up. There's as much left over at the end as we started with. They increase the equilibrium yield of reactions. Well, in equilibrium, no, they don't. They allow to get to the point of equilibrium quicker, but they don't change the yield. They don't change the ratio of reactants and products. So that's not right. They provide a different reaction pathway. Well, that's exactly what they do, isn't it? They provide an reaction pathway with a lower activation energy. So let's check what I was asked to do. I was asked to tick 2 boxes, and it's that, and it's that. 1.7. Figure 12 shows a reaction profile diagram for a reaction without a catalyst. Draw the reaction profile diagram for a catalyzed reaction, and then draw and label an arrow to show the activation energy for the reaction without a catalyst. Right, so taking the first one first, the reaction profile diagram for a catalyzed reaction. What a catalyst does is it reduces activation energy. So this hump here is the activation energy to get from reactants to products. If I add a catalyst, I reduce that activation energy hump. I reduce the size of the hill I've got to climb over before my reactants become my products. So if any line like this, where the hump is clearly smaller than this hump, is going to get you the first mark here. The second mark is a little bit harder to get, and most people, there are a lot of people who had the right idea but were just a little bit careless with it. You've got to show the activation energy for the reaction without a catalyst, so it's for this line here. And you can either do it at the side or in the within the curve, but I do it at the side like this. I'm going to draw a line like that, which shows that I'm taking the top, the very peak, the highest point on the energy scale, and then I'm going to draw a line like this that clearly goes from that line, the reactant line, to the top there, like that. And I was asked to draw it and label it. So I now have to draw a label line, and that's the activation energy for reaction, no catalyst. Right. If we just did this, right, where the bottom of the line is a bit vague and the top of the line is a bit vague, and our arrow was and our label was missing, although I can see that you probably know what you're talking about, you probably won't get the mark, because do remember, the examiner hates you. That was 14 marks in total. There we go.